here we go. All right, so I'm making this video, which means that you can watch it again if you want. If I go too fast and you want to see what was on the page, you can do that. All right, so we started looking at matter, all right, and the amount of substance in a piece of matter. We looked at volume, particles of matter, etc. So let's go to this link right here. And one way to study these is to do the flashcards. All right, so motion of particles. And then the next one was about the physical properties. Let me try this a second. Okay, I was right. Bunsen-Burner. Spectral lines. Is this right? I'm feeling like this isn't right, so give me a second. Yeah. Why is it taking me to that one? Okay, here we start with mass. All right. I'm puzzled because it looks like it's doing a different one here. And I have done this already once today, so I'm not sure. So this is a different set that it's showing us instead of these. All right, so what I'll do is make these large instead then. So we talked about particles made of matter, what matter is. So I will be looking for definitions of these words. Don't sit and talk, please. We're having a review, so get this out. All right, so mass divided by volume, that ratio is called density. All right, we've analyzed experimental results like we did with the mass lab. Conclusions, the answers to the questions we set up at the beginning. Procedure, like the one we're doing for separations, element, compound, pure substance, which we practiced quite a bit at the beginning. What's a mixture? Now, these are two words that we didn't focus too much on. A solution, like salt water and sugar water, just look like water. But if you have three glasses, one that's water, one that's sugar water, and one that's salt water, they all look alike, but they are different. These are called homogeneous mixtures because they only look like one thing, and it happens to be the solvent water. But you could tell that salt water tastes different than sugar water, that tastes different than water by itself. All right, those are called homogeneous, means they look the same. All three look the same. You can't see the other, you can't see what's mixed in. A heterogeneous mixture means you can actually see more than two or more things. Like a tossed salad would be an example of a hetero, different, that you can see the different things in the mixture. All right. Now, we talked about filtering, decanting, distilling, evaporation, separation, atoms, formulas, molecule. A kilogram, our machines, our balances measure in grams, and the most they can measure is about 300, almost 400. All right, grams, which is not as much as a kilogram, which means 1,000 grams. Kilo means 1,000. So metallic elements are all these green ones on the picture. They make up most of the periodic table. The nonmetals are the orange ones. All right, so we'll study that more later. And we know the periodic table. All right, states of matter, you tested out on that, so what solid, liquids, and gases. So the motion of particles, that in the solid state they vibrate, moving up and down, up and down, up and down, up and down. In a liquid state, though they move, they're able to move. They're still attracted, but they're able to move a bit. But in the gaseous state, the millions of molecules move rapidly away from each other. And there will be points at which we use that constantly, the idea. Physical properties of an element or compound, a characteristic of a pure substance that can be observed. For example, will it dissolve in water? Will it heat to change its state of matter? Does it have a density greater or less than water? Is it visible? Does it have a clear color? Is it magnetic? Does it have a melting or boiling point? In, the range of environmental temperatures we have. All right. So that's a physical property, then Bunsen burner. All right. So these are the things that we were gradually getting to over the course of the unit. All right. And what I'm going to do is go to I am in the content library. It looks like I stole somebody's stuff, doesn't it? All right. So the first things we did in this unit that is about particles is trying to figure out what do atomic and compound particles look like, and what does the word purity mean? So here's what we had. The conclusions that we would answer at the end of this is, what is an element made of? Well, how is an element of copper different from an element of iron? What's the definition of a compound particle, and how do we know what it's made of? What does the word purity mean? And can you recognize the substance as an element, a compound, or a mixture of elements and or? So we talked about there's 118 known elements. They differ by their atom, but all atoms are spherical. They're just different sizes, and they contain differing numbers of subatomic particles of protons, neutrons, and electrons. All right. We talked about the fact that compounds have a chemical formula because two or more atoms are stuck together in a particular way, and we need the formula that tells how they're stuck together. And we did the examples of small compounds like H2O, where there's just 3 atoms in water, and there's just 2 atoms in NaCl. All right. And then we have a much bigger, table sugar is a much bigger compound. And because it's a carbon-hydrogen one, it's called a molecule. That's the specifics. So all of these things I've shown you in the room, up here and around the room, are molecules because they have carbon-hydrogen backbones. All right. So sugar is a relatively small one for an organic compound. But the formula tells you how many atoms of what kind are bonded together. All right, so, but there's even huger, like the milk protein casein, C81, H125, huge numbers. 22 nitrogen atoms, 39 oxygen, and just 1 phosphorus. And bigger than that, DNA, RNA. All right, we saw that atoms have a 0 net charge because they have the same number of positive charges inside the atom as negative charges. We saw that compounds are also neutral, and we saw that, let me put this, it's because a chemical bond is made of something like this, where opposites attract. All right, opposites attract. So everybody should be with me on your pages that are just like the ones that I'm going over. Okay. Now, when are we having our test? Tuesday. All right. And then over here we had all these questions that you answered. And then we went in these and we saw that this first one must be an element because all the atoms are alike. Similarly, all the atoms are alike in this one. So this must be an element. But what's different is each atom is paired up with another. And that's because there are 7 diatomic elements. And this is one of those. All right. Then we saw, let me come over here. All right, then we saw that this is a pure compound because there's only 4 particles and all 4 particles are identical. So this would be called a pure compound where there's a red one and there's one of those and that there's a green. So the formula would be red 1, green 2. And this is the compound. So compounds have formulas. What's the formula of an element? Neil, what's the formula of an element? Just its symbol, unless it's one of the 7 diatomics. And then we got to this guy. Oh my gosh, there's somebody blue and orange. There's a particle that's orange and red. Then there are 2 red atoms. So this is not pure. It's clearly a mixture. So purity only depends. It's not good or bad. Purity means there's only one kind of particle. But this is not pure because there are 3 kinds of particles. All right? We may want the specific mixture. Maybe we don't want one thing 100% pure. So it depends on what we want. So purity can be good. All right? And impurity can be bad. But it depends on what combination of things that you want in a mixture. All right, then I saw that you were really good at states of matter, solid, liquid, and gas for the most part. And then you were supposed to say which of these is an element and what is a compound. And so here we saw, I'm going to circle all the ones that are elements, only have one symbol. All right, so these have to be an element. All right, whereas those that have more than one kind of atom must be a compound, and they're bonded together. All right, Kool-Aid does not have, and Kool-Aid mixed in water, neither of them have a formula. Kool-Aid doesn't have a formula. It's just a mixture of sugar and flavorings and colors, most of which are artificial. All right, so Kool-Aid powder is just a mixture of those things, and then we add water to it and make a solution. So regardless, it is a mixture. You cannot have a formula for a mixture. You cannot have a formula for a mixture. But you can have something. You cannot have a formula for a mixture. All right, but what can you have, Daniel? Did you say you know what you can have with a mixture? Oh, yeah. Do I have a card? But maybe one in there. Most likely there isn't, because I don't think I have a card about it. If there is one. Thank you. That would be great. No, but you know what you do have? Who knows the recipe for gorp? Gorp. All right, what's the recipe for gorp? Just give me one. There's many. All right, teaspoon of salt. All right, gorp stands for good old raisins and peanuts. So tell me how much? All right, we want 1 cup of peanuts. Do we want a half a cup of raisins? Do you want as many raisins as you have peanuts? I want 2 cups of M&Ms. And I want 1 cup of pretzels. All right, so in mixtures, what takes the place of a formula are all the different recipes that you can make with these combinations. I'd actually get rid of the raisins and just put in M&Ms. All right, so you can't have a formula for a mixture, but you can have a recipe. So alloys, for example, like steel. So there are quite a few different recipes for the alloy steel made from primarily iron. There's probably 50 different recipes for making the alloy iron. Usually it's iron and it is carbon, but then there's also chromium sometimes in it, etc. All right, so there's different kinds of steel because there's a different recipe. But there's no formula for steel because steel is a metallic alloy and it's a mixture. All right. We got so excited that I taught you how to first interpret diagrams and then to start drawing them yourself. So we looked at these and we saw, oh, well, look at, there's black atoms and there's white atoms. And in fact, every particle has one of each. So this is a pure compound made up of 5 U-1, W1. That would be the compound's formula, wouldn't it? One black one, one white one. This one, all the atoms are identical, but they come in pairs. So this must be a diatomic element. But we know it's an element because all the atoms are the same. Oh, no. We have 2 different kinds of atoms, and then we have 2 different kinds of particles. So see here, we had 2 different kinds of atoms, but all the particles were identical. Here, we have 2 different kinds of atoms, but we have 2 different kinds of particles. All right, so we have the black 2 diatomic element, and we have the white 2 diatomic elements. All right, so the drawings that you make, we can often just show by making one white and the other the color of an outline. All right, so then you were just going crazy drawing them. All right, where titanium is on the periodic table and it's not diatomic. Silver is on the periodic table, so it's an element, it's not diatomic. All right, and so I'm going to make it look different than titanium. All right, now nitrogen is diatomic, so I'm going to show it like this. All right, now when we got down to sodium and calcium and silver, all of those are elements on the periodic table. None of them are the diatomics. Then we started talking about water. All right, the formula says 2 hydrogens and 1 oxygen. So we know that must be the oxygen, and this must be the hydrogen. MgCl2, it looks a lot like water, doesn't it? In that there's 1 magnesium and 2 chlorines, and usually if there's just one of them, we put them in the middle. And then here we have AlCl3, etc. So we got down into methane, salt, NaCl, and bromine. All right, so because we're making a video, you can go back to any of these pages that you want to. All right. Now, I'm making this video and putting it into my YouTube channel. All right, so if you have access to YouTube, then you have access to this video. And unlike when we watch it in Edpuzzle, you know how it won't let you go ahead? But this will let you go anywhere you want in the video. I'm also putting one in Edpuzzle because there's a few of you in every class who have been denied access to YouTube. So I have it in Edpuzzle. So if you can't open the YouTube, you can go to Edpuzzle and just open it. And it's not going to restrict you either. I made it fairly open. All right, now, so here we had our balance, and we got down to our data, all right? All right, the mass measurements was 0.99, 2 places past the decimal. But when I did it with 3 places, which I routinely do, all right, the mass is 0.990 because it was right on this 9. All right, so that's how I meant to show you. But I always read 2 3 decimal places to the right. All right, 29.215, 9.640, 13.195. But then what we were going to do is compare yours. All right, so this is the teacher value. All right. So this is the true value here for the paperclip. The rest of these were not standard. They weren't not a standard object, so we can't say that they should all be identical. All right, over 20 years of getting them, we've bought many different lot numbers of them, but we only had 1 lot number of paper clips, so that's why your reading should be just the same as mine. You know, close. So let's go now. Let's hit the back arrow and go to the collaboration space, and here's where all of your data is. So every group entered their mass readings in the collaboration page, all right? And then, after you entered it all, I found the class average by putting the data into Excel. All right, and so your average was 1.05. So this is the class average, and this is the teacher value, all right, in every case. All right, so first, if you compare yours to the class value, you compare the class average. If you're comparing how accurate it is to this, you would compare it to mine. All right, now find yourself. All right, I want you to see how close were you to the average. Find your reading. Let's just pick Adriana and Yeslin. So they're right here. They got 27.00. The average was 27.85. I got 26.85. All right, so they're pretty close to the teacher value. They're closer to the teacher value, you might say, of 29.215. All right. Then when you look at the funnel, and we pick them again, 9.3, all right, the true value was 9.64, and the class average was 9.1. So they are closer this time to the class average of 9.1. So the way that you decide if you have a good measurement is either it compares to the class average, or it compares to what the teacher got. Okay? So knowing that, and now knowing what you got, and you can go back and forth between this page. All right? All right. All right, so now I have these two side by side. And what I can do is, and I want to do the lab. Come on. There it is. All right. I keep goofing up. There, let me just make that smaller. All right, so you can do something similar. And what you need to do is answer these questions then. The conclusions were, how does your team know if the 4 measurements are good or not? All right, so answer question 2. So we just ran out of time, so we didn't really have time to do the conclusions. Is that correct? Did some of you have things written here already? Okay, so go ahead now and do this, please. So compare with what you had over here in the collaboration space and decide how you knew your team had 4 measurements. Maybe one was good, really good, the others were okay, and one was pretty bad. All right? So bad would mean far away from the teacher's measurement or the class average. All right? Do that now. Make your judgment. So I'll give you a few minutes. Explain how we know that tiny particles of matter have weight is the next one. This is a little bit odd because we had to measure the big stuff, right? In the lab, we have to measure. So how many particles were you measuring in a paper clip, for example? Will, how many particles were you measuring in a paper clip? Millions, billions. Yeah, so there were millions of, we'll just assume scale, of particles of iron in our paper clip. I'm going to have to write smaller, aren't I? All right? In our paper clip. So, does that prove to you that, okay, that needs to go down there. Does that prove to you that a particle must have a little tiny mass? Well, does that prove to you that a particle might have a little tiny mass? All right. All right. So explain how we know that tiny particles of matter have mass. Explain that based on when you measure paper clips. That's fine. Yes. Thank you. So go ahead and then make an explanation if tiny particles of matter have mass, or what we in the English language often call weight. The third one was explain how we know that a group of particles must take up space. So just using Will's ideas that the paperclip took up space, we know it did, right? All right. So how do we know that a group of particles must take up space? This has to do with particle arrangement. Thank you very much. With particle arrangement. Yeah. How the particles are arranged is important in volume. Well, just bring it up here, because, yeah, bring it up here. Yeah. So this is the separation. So let's go to it online. Let's go to go away thing. All right, try going online and seeing if you can see it there. There is a way to go to it to the online version, but I forget what it is. Usually there. Yeah.
One note online.
Yeah, one note. Hopefully that'll work. We'll see. That's what.
The treat.
That's what.
You
Not unless you changed it. If you didn't change it, then it's the same. Okay. So hopefully the online version. All right. That we will see then in your notebook or something. So we are on this lab 815 here.
on August 15th.
Yeah, it was actually supposed to be September. No, it was August 15th. This is from a long time ago. Okay? Yeah, so you have it here. And so you can use it here, but then keep trying to open it in the desktop app as well to see if it will.
So can I press open the desktop and I get everything in there?
Well, since it's telling you that permission thing, I fear that you're going to have to be online. So IS hasn't fixed it. They just keep telling people to go to.
How do I get to that?
So take a look right there. These questions right here.
So why is it place?
Well, because this is a unit test, Brad. Yeah. So this is a unit test. So it's over since the first day of school, or really the first week after that. Yeah. So that's why this was such a long time ago.
Did you answer that?
No, your answer. I'm just giving you. So you don't have any data, but you could get data from your partner. Okay. So maybe you were here, maybe you were not. I don't know. Because you haven't missed that many days, so it would be the 15th or 16th. All right. So how many particles of sugar are necessary? So remember, we held up our spoon pretending to put it on our cereal, and you were trying to tell me how many particles should be on that spoon. And like Will said, there must be millions of particles of sugar, individual particles of sugar. The number 7 is about mistakes. So here's some potential mistakes. So decide whether they would cause a higher mass or a lower mass. So if you did not zero it, would that cause a higher mass or a lower mass? Or would it cause either one, depending on what the zero was? What about if the object was wet? Would that give you a higher mass or a lower? If the pan was wet, would that give you higher or lower? If the pan was dirty, would that give you a higher mass or a lower? So that's what 7 is talking about. And so this number 6 is asking, so what are the ways in which you're careful? Another way to paraphrase this, or what are the ways in which I was careful when I balanced? All right, that would be another way to answer this question. And we learned about mass measuring mass, because this will be the most important and most consistent measurement that we take in chemistry. Right? So we measure the mass of everything, just like Lavoisier did. So that's why this is the most important instrument in the lab for us. All right. Now, after we did that, I asked you to do a pop quiz and show me that you could draw elements and compounds because you understood them well enough. All right, so then I showed you the key that elements like silver would be made of 5 identical atoms of silver, whereas carbon would be made of 5 identical atoms of carbon. Then we got to water, which has a formula of H2O, so that tells you how to draw the particle. Then we had calcium chloride, and we saw, gee, those look very similar. And then we had chlorine. All right. So that was your pop test worth 10 points. Some of you, because you were absent that day, or because you didn't like the score you got, there is an 8/22 makeup pop quiz. So if you haven't done that yet, you can do it and then send me an email that says I should grade it. All right, and then I'll grade the makeup one. So the one that you didn't do is locked. So that's why you will have to, if you miss that assignment, you'll have to do the makeup one. All right. Then we did a total diversion and we started discussing tap water. Is it safe? We spent an entire week on this because we wanted to get at scientifically, how do we know if the water is safe or not? By the end of the week, we found out that actually our water is tested constantly by the City of Mesa Water Department. All right, and up until that point, very few people knew that we actually even have anybody in charge of what's in the tap water. So we started, and it was about, in all 3 classes, it was about half and half. All right, then we started looking about sources of water on Earth, and then we found that, well, a lot of our water is invisible because it's underground, so that 1/3 to 1/2 of the water that we drink is groundwater buried underground in layers, between layers of earth, and that's built up over time. Then we discovered, despite the fact that ocean water is so plentiful on the earth, it's not cheap to get the salt out. So right now, hardly anybody uses seawater, ocean water, to get drinking water because it's such an expensive process. But all over the world, companies are experimenting with this because of the danger of groundwater loss. Companies are trying to figure out what's the cheapest way we can reliably get the salt out of ocean water and make it taste good. All right. So we were really finding out a lot about groundwater and the fact that by 2040, when you guys are in your 30s, the groundwater beneath Phoenix may be gone or may be so low as to our need to import water from the ocean. All right. So that's something that will happen in the next 20 years of your life. And mine too, assuming, I live to a ripe old age. So that's why we talked about groundwater. And then we got the Mesa Water Report, and you saw, oh, well, at least they're on top of it. Look at all they do. They look at bacteria, fertilizer, they test for lead and copper. If whatever it is in too large a quantity, they dilute it with water. We found out we get our water from the Colorado River, the Verde River, and the Salt River, and then it gets blended with groundwater. We found out that there's all kinds, parts per million, parts per trillion, parts per billion, which is 1 gallon per billion gallons. We found out that, well, yeah, we're allowed to have these contaminants in water, but at such tiny, tiny amounts, they won't hurt anybody. So that's what we found out. And then we found out that bacteria is chlorinated or ozoned. You can also O3, mix it with ozone and kill bacteria and viruses. Then we saw there are ways to even get out the dead bodies of bacteria and viruses out of our water. All right, so we found out that our water indeed was safe to drink. We may not like the taste, though. And then we found out bottled water is judged the same way tap water was. So what we have in bottled water is just some other city's tap water that tastes better. That was shocking. That's kind of shocking, isn't it? And it's probably a blend of a variety of cities' tap water. All right, so it's not that it's so cleaned up, it's that it is diluted. It can be filtered if there's something obnoxious in tap water, but most tap water has already been tested and filtered if it's tap water at all. All right, so this was kind of shocking news. We knew our tap water wasn't pure because we know it has minerals and other things in it besides water molecules. All right, so we decided what we didn't want in our water, and then we found out that's what the city of Mesa was trying to cope with. Those were the things they were measuring. All right, then we got to separation of mixtures that we were talking about yesterday. This is some of my best art, guys, I have to say. Yeah, really. I mean, even I'm impressed, and I'm seldom impressed with my own drawing. All right. So we were looking at separation of mixtures yesterday and all the ways that we can separate. And then our lab that we will do Monday. So you saw that the equipment for that just arrived from somebody else's class who's been doing it. But the only people who will be able to do it are the people who have had their parents sign their safety contract. All right, so find your safety contracts. Find your, let me go to Daniel's. Yes, because Daniel actually had somebody sign. Here it is. This one? This one right here? Yeah, okay. This is the one above it? Okay. Okay. Now let's see. Let's see what that looks like. Oh my gosh. All right, now I only see one problem, Daniel, is those look like initials to me rather than a signature. Yeah, no, those are initials. That's not a signature. Yeah, a signature has first name and last name written. All right, those are initials. So see, I need to know what your parent's name is. So that's the reason why that isn't very helpful to me. So go ahead and have your parent sign it, first name and last name, not just initials. Okay. Yeah. So like if you sign bank documents, so there are places for your initials and there are places for your full signature. Okay. That's the difference. Okay. So those of you who have this signed by your parents will get to do the lab Monday. Now, if it turns out that there are too many people who haven't, I'll devote class time to something else we can all do. All right. And Tuesday, then we'll have the test. All right. Does anybody have questions about that so far? Will you just spend the rest of the time trying to think of what do I need to do to turn in? Because, of course, I'm grading for the weekend, right? I'm going to be grading. And we hope that I'm going to be grading better than I have been, so I get a lot of this done, right? We hope. And so I'm going to sign off now.